So just a relatively short video then on how conservation of energy can be used to set up, say, equations that can be solved for different parameters as long as you're talking about conservation of energy. So we left one of the last videos with the fact that for these simple mechanical systems, the total energy will always be a constant. Always going to be the same number. We're not going to deal with systems where we're unable to account for where the total energy of a system might have gone. And as we know for these mechanical systems, that would just be equal to the kinetic energy plus potential energy. So because this is always equal to a constant, the real power in conservation of energy is the constant is always equal to the sum of the kinetic and potential. We sort of rewrite this a bit to say, well, as long as we have kinetic and potential energy, and we know that the sum of these two is always going to be the same number, we can set that equal to another set of potential and kinetic energies that might appear later on in the problem. But again, it might look a little weird drawing this, but because this sum of kinetic and potential is always equal to the same number, and this sum of kinetic and potential is equal to the same number and the same number, the two sums can even be set equal to themselves because both of these are always equal to this total energy right here. So we're just choosing to disregard the total energy and set the two sums equal to themselves. But we have to be a bit careful now because they're not the same kinetic and potential. We'll say this might be the kinetic at point 1 and that might be the potential at point 1. This would be the kinetic at point 2 and that would be the potential at point 2. So that's the real power of conservation of energy, is in an equation just like this. And to sort of illustrate this again, we can return to the ball flying above the ground. So say the ball is being launched right here above the ground, and it's doing something like this. It's flying through the air like that. And suppose we want to know, for instance, what the speed of the ball would be, say, right here. Not quite at the top, not quite at the bottom, just sort of somewhere midway in between. Well, according to conservation of energy, what we sort of have 2 points, don't we? We have a launch point right there, point 1, and we have some other point of interest here in point 2. And conservation of energy says the sum of kinetic and potential over here will be equal to the sum of the kinetic and potential at that point. So we can just go ahead and set up an equation and see where it might take us here. And what we notice about point 2 is because it's off the ground now, the ball has developed some height h above the ground. So that will contribute to the potential energy at point 2. So let's see what we can set up then. So we just sort of fill in this equation here. We notice that the kinetic energy at point 1 is 1/2 m times v1 squared, where I'm being very, very careful with my subscript and saying, well, v1 is the speed at point 1 where the ball is being launched. Now, there's no potential energy here. I'd like to add a plus potential term, but there's no potential there because the ball's on the ground. And so if I just continue this then, the kinetic energy at point 2 would be 1/2 mv2 squared, because as it's sort of zipping through the air here, it has some speed v2. And the potential energy at that point now, it will have some non-zero potential energy because it has risen h above the ground, so we should sort of label this here as an mg times an h2, noting very carefully that the height here is the height at point 2, say not at point 1. But if you look at what you've done now, you've formed an algebraic equation based on the principle, conservation of energy. You can simplify it a bit. 1/2 mv1 squared equals to 1/2 mv2 squared plus mg times h2. You can put a box around this and we'll stop about here because we don't really know what exactly the problem might be solving for, but in the case that we hypothesize here, we might have thought, well, let's see if we can solve for v2, the velocity it has at the second intermediate point that the ball is on its trajectory. But we have to, of course, know, for instance, a bit more information about it, like we have to know what h2 is here. We have to know how high the ball is right here at point 2 before we can solve for the velocity like that, because we only have one equation, we need only one unknown in there. So be things as it may, here's a simple algebraic equation that relates the velocity at point 1 and the velocity and height at point 2. So two different points along this object's trajectory now have a definite relation between them. And here it is. And so it might be possible to solve for one or other variable depending on what your needs are.